That's what it is. And the chokes are. We don't get
Everybody, please take your seats. Okay, next speaker is Fedor Bogomolov, the title of his talk, Symmetric tensors and the geometry of subvarieties in projective spaces.
Thank you. So my talk will be devoted to basically some results and maybe mostly conjectures, which are naturally follow from our article with Bruno de Oliveira, which was published in 2008. So it's symmetric tensors and geometry of subvarieties in PM. However, the book is related to Fedor's book. And therefore, I want first to say congratulate him. It's great to see him in the press. So I wish him many years to come. And I must say, I know Fedor by far longer than anybody. I calculated today, it's 51 years. So, and the reason for that is simple. Fedor was in the famous, high school student of the second, so-called second physical mathematical school, and I was a student in the seminars of Lincoln, who decided to, who was invited actually in '64 to bring up to basically to enhance the mathematical education in the school. And since he had these seminars and he was very popular professor at the university and also liked to do things well, so he brought up most of, I won't say most of the mechanical mathematical faculty, but a big chunk of mechanical mathematical faculty to teach at the school. And I still remember, so most of the people, at that time I was actually a high school student. I was in 11th form, and so for the first, I think it was during the spring semester, the whole year, I don't remember, but I was together with Lincoln, we had a seminar at Fedor's class, actually. So he was a student, and I remember him in a school form uniform. So at that time. So and after that, this continued for several years. I stopped doing it in a couple of years, and then we encountered from time to time. But then, what happened next time? His name kind of came up with his great result about tangent and secant variety. And in fact, again, this was I kind of felt it was I hadn't heard it from Fedor, but it was a talk of Danilov, who is not here, unfortunately. He works with you. Okay. Danilov works at the same place, but it was his talk, and at the school, at a sort of, I'd say, difficult to say how to call it. It was a school. The life at that time, the mathematical life, existed kind of in several different dimensions. So, for example, there was a lot of life outside of official life. So, for example, for about 10 years, from 1917 to 1980, we were organizing some kind of small mathematical school regularly in the spring in my village house. It was in algebraic geometry, initially in topology and so on. So it was usually it's not a great place, but so it is. So it was about 10 people. But then, from beginning of 80s, we started to organize such schools in Lithuania with the help of Lithuanian students, and it continued for about 8 years. So every spring, a bunch of algebraic geometers was going to Lithuania, to Trakai, to some other place, and everything was kind of done privately. No administration involved. So there was a combination of swimming and lectures, and one of the lectures of the Nil, if I remember, was exactly devoted to Zach's rocks, and then there was a lot of discussion on what to do next, and so on. So it was a pleasure to kind of bring it back, all these memories. And Daniel, as everybody knows, is a very great exposer, so he's inside it was even kind of better. So we tried to see some corollaries, and it was clearly a great result at the time. And my talk actually is not, but is also related, and I will tell how. Okay, so first, there are two things I'm going to discuss. And one of them is that, two topics essentially, which are related. So one of them is something I like, that means symmetric tensors. So what I'm looking at smooth subvariety in here, and dimension of x is sufficiently. Dimension of x, usually we need more than half, and in fact, most of the results of conjectures are hold exactly in kind of, I would say, Zach's boundary. That means 2/3 n minus 1. Yes? That means something like that. So we need something like that. The subvariety has to be in dimension has to be close sufficiently to the dimension of projective space in order for this to hold. And what we are looking at, we are looking at the space of symmetric tensors. And we are trying to understand why this space is not given. So the question is, so what is this space? What is this, let's say, algebra? And basically when it is, first when it is non-zero. And so x is smooth. X is smooth. So this is one question which is kind of coming from the, well, I used to work with symmetric tensors from time to time, and so this is much more natural for me than projective geometry, standard projective geometry.
Is it all 1
Sure.
11?
Не понял.
Is it all 1 or 11?
Где его?
Он
Никаких
омега-1
больше
на что?
единиц нет. Чего?
Омега-1 на что там это?
Омега-1 тензор O1.
It's a bracket, there are 3 brackets.
Много брать. Омега, правильно. Омега, O1, правильно? Омега-1, O1. Все правильно. Okay. So another question is about quadrants, and actually, from it's not exactly related to the topic of previous talk. However, what I'm looking at, so for any variety x again, I want to, so we can define, so Zach was looking with T of x, so tangent map. So essentially you have x inside Pn, and then you have a map, let's say, I would write it T bar over x, so you complete H tangent space to this T, okay, let's say, okay, next, so it's pk, and then you have a map to Pn. So there is a map as the standard argument. The theorem of Zach is that if we are in that dimension, in that range, then the map is surjection. Okay, so essentially surjection plus something is possible before what we need later, and then you can define you can define a variety CF. It's not a very good definition. This is slightly different than that. So this variety consists of lines. It's of lines. Lines L equal T bar. Yes, Lx. So lines through point x, such that Lx is tangent. So Lx is tangent to x, and plus Lx intersects minus x non-empty. So that means that the lines which are tangent and then intersect at some other point.
So one x is small and another x is capital.
Sure. Add the x, ex first. No, yeah, that's a bad notation. Okay.
What is
I don't know how it came, but at some point.
So the question is, what is x minus x?
So what I want to say is, you take line which is tangent at point x and intersects x. So this is x.
But the one axis point and
This is L. This is L. Yeah? So one line, you take lines, take a union of all lines, which are first tangent to x at a point, and then but intersect x at some other point. Something. So certainly, subvariety, this subvariety lies inside what T bar.
it's a union of this line.
It's a union of all lines, so it's a union of all such lines x. So it's a union of all such lines. Okay, so in some cases it's just the same variety. For example, if you take quadric, then it is the same. So notice that if you take quadric cube, if x is cubed, then Cxx is equal to. And the same holds for the intersection of quadrics. Nature. Yes? And then, certainly geometric conjecture is that, well, that if you begin with something which is sufficiently big dimensions of conjecture, is that, and we proved it with Oliveira, but for small numbers. We couldn't get to that. If Cxx is equal to first is equal to x, and x is smooth, then or sufficiently good. Smoothness is too strong, sufficiently good, then x is intersection of qi, but not complete intersection. Let me say that it is just intersection of qi. Yeah, so basically it's a component, let's say, x is a component of the intersection of qi. So this is a conjecture, and we proved it sometimes, and there were some ideas, however, we ran into difficulties. And the second question is that, okay, so now assume that we begin also with something, and then we take maybe dimension x, we need dimension x greater than 1, yeah. At least greater than half. We want to increase the variety to increase. So at least to be sure that we will add something. So for that we need dimension to be greater than half. Yep. And then what I want to say, if we take, let's say I would apply it many times, then we obtain intersections. So that's a more precise one. So this is a purely, I would say, tangent question. Yes. Question about some slightly peculiar question about tangent varieties. So it's not exactly tangent space.
So if it's the second array, so it's a complete intersection of correct, or it's a
No, just intersection. Just intersection. For example, a good example, let's say if you can take intersection of 3 quadrics in P5, which is good enough. So I don't claim that the number of quadrics is equal to codimension, just the intersection of quadrics.
But such lines are a special case of trisecond lines.
Yeah, exactly.
So if you have that, you can put the same equation for trisecond.
Yeah. But the point is that exactly the trick, which is similar to yours, will tell us that trisecond lines in some cases are the same as this. It's exactly your lemma. That's why. Yeah. And I will explain how I understand this lemma. Yeah. Okay. So what happens here? So what is the relation? There is a relation. In fact, what I can say, if dimension of x, so suppose we have P, suppose we have a map, P bar of x maps to Pn, yes, and so this condition n greater than, greater than 2/3 n minus 1 guarantees surjection. And we gave a proof. I think that for this kind of result, we can also show the generic fiber is connected. I am not, generic fiber is connected. Okay. So what it tells me, it tells me something about this kind of tensors. Namely, you see, what is a symmetric tensor? Symmetric tensor is just a function on a tangent space, holomorphic, homogeneous function on a tangent space, and these are functions on tangent space with coefficients. But when you embed Pn, tangent bounded to Pn is kind of almost projective G, but almost. So I recall that tangent bounded Pn, T of Pn, well, there is an exact sequence for 1 n minus 1, 2, 4. Yes. Okay, so I would like to say that this is kind of enlarged tangent bound. So nature enlarged. Because then, if I take 4 minus 1, it will be 4 n plus 1. So then I can say that instead of looking at kind of holomorphic sections here, I want to look at, okay, so this will be my bundle, and now I want to say that if we have x, then, and restrict everything on x, then there is embedding of a tangent bundle, the T of x here, and then we have T bar here, T bar x, so we have, and also I will take 4 minus 1. Okay. So now we are getting closer.
What is T-tile?
Sorry?
What is T-tile?
T-tile is extended tangent bundle. I extend, so you have a tangent bundle, and you just induce your tangent bundle of x embeds into tangent bundle of projective space because it is embedded. And then you can induce this extension into this extension. What the result? What are we getting from this? We are getting that now this Tx embeds into 4 n plus 1. Yes. So we have an embedding. An embedding into trivial bundle certainly induces a map from tensors, so from symmetric tensors of 4 n minus 1 to symmetric tensors of, okay, so I will erase this, okay? To symmetric tensors of x, let's say omega 1 tilde dual of x. And now this tensors here are tensors on projective space. It's a trivial bond, so everything induced from the point. So the tensors here are the same from the point. And therefore we can say, so, but now exactly, so we have this map. So if this map is surjective and the fibers are connected, yes, then we can say that this map is surjection. if the map is if this is 1, 2, 3, 1, 2, 3.
So how did you get this map?
Well, you have embedding, yes?
Yes.
Yeah. You have embedding. So we have embedding of this. So this is a dual. So we have tx maps into ON plus 1. Yes. Then omega tilde, there is a map of ON plus 1. And then you take symmetric power. So symmetric powers are subjective, and you can easily realize that, easily see, you see, so in particular they are basically induced from here. So that's a claim that all tensors are induced from here, and moreover, it's embedded.
But did you take a symmetric power on the right hand side?
Yes, on both sides.
No, I mean down.
Oh yeah, sure. Yeah. Minus 1. Okay, I take O minus O1. Okay, so we are very close to O1 already. So we have this tangent mapping. We are very close to O1. However, you see, it is much, how to say, this bundle is bigger. Yes, this bundle is bigger. So for a symmetric power, we certainly have for symmetric power, we certainly have sorry, wait, yeah. So we have a dual. So this is SM for omega 1 tilde. This is tensor O1. This one, and here it embeds. So there is an embedding. But you see, the fact that here we have a lot of tensors, for example, doesn't tell us that we have a lot of tensors here. And in fact, we can show that, so now we can say what means for these symmetric tensors for an element here to come from here. And now there is a simple, as it happens, there is some criteria. This is symmetric tensors, big power. You can view also just as a function on Pn. Yes, so we induce it from Pn. So if you have x inside, so x is inside Pn, x is inside Pn. Then what is the whole space? The whole space is like, so it's like function. So here is a tangent bundle at point x, and the whole space is kind of a fine cone over Tx. Yes. So it's a fine kind of extension. So now we can see, I don't want to get into really difficult details, but however, I want to say that these elements here are exactly tensors, so functions. So essentially, these are functions, which are homogeneous, which when you look at them at x, along x, they're homogeneous in every tangent direction. So you see, you take polynomials. So these are polynomials. You can view this space as a space of inhomogeneous polynomials. And this part are homogeneous polynomials with respect to point x. So therefore, you have this locus. So suppose you have now, notice, well, what I did is I just shifted from, so what I'm looking now, I'm looking at functions which are on a tangent, which are restricted to a tangent space at point x are homogeneous. Okay, so that means if you take t, so now I want to say that, so the locus of omega, intersect with t of p, and it has to be a constant. In particular, yes, if we have a line like that, yes, then the corresponding function has to be trivial, because it has to be homogeneous. So therefore, I hope I'm not. Well, unfortunately, only thing I cannot try to illustrate it. It's not very long, but so you see, that's kind of geometric way to see the elements which are becoming, which are actually produce symmetric tensors. These symmetric tensors with coefficient values. So therefore, it implies that this Cxx is embedded into locus of zeros for an element for f, viewed like so for element f, which is viewed like this one. Yes. Maybe so f. So you can view h such function f also as element or in the children. Okay, so this group has Cxx is embedded into the locus. In particular, if Cxx is equal to here, which is normal, then under this condition, under 1, 2, implies h0x Sn omega 1 or 1 is 0.
Do you have any idea when it happens?
Sorry?
Do you have any idea when it happens when Cxx equals Pn?
Usually.
Okay, so it's
Apart from, so in fact, what I was talking about is exactly was that. Yes, so if it is not so, for example, first result, if it is not so, then x is inside 40. And in case of hypersurfaces, this is exactly the case. So if x is a hypersurface, now Cxx is equal to Pn. Well, you need dimension, yes, greater than 2, unless x is a 2. And the general condition is that it should also be true. Yes. So, and in fact, what we have proved with Bruno de Rivera, that it is a case of codimension 2. And since we were trying to do more, but I think the result of Quark, who is here or not, I don't know, who proved something about dimensions. And here I want to say how what actually happens. That when we, so why is it related to Zachson? Okay, so first, so we consider, so when we look, we can view such line as a particular case of so-called trisecond. So this line, this kind of thing. This is trisecond, and this is degenerated trisecond. And in many cases, like codimension 2, we show that trisecond, so we can say tri t is this one and trisecond are this one. And in many cases, we can say that triseconds, that these varieties are the same. The same in many cases. Which is complete analogy that secant is equal to tan. X in many cases. And the reason for that, and in fact how you can apply Zach's argument to many other cases, to many other families of curve, is the following. So suppose you have, suppose you know that, suppose you have a generic point such that, so first assume trisecond x is big. So it subjects onto plane. Yeah. So that means through any point, and through any point, there is a family passing through this point. There is at least one dimension for a generic point y in here, not in x, yes? There is at least one-dimensional subvariety of trisecant line, of tri-x passing through it. So that means there is something like a cone here. Okay, now I want to show that then there is a isomorphism. And the reason for that is kind of trivial if you think. Just look at this. So there is a, so what I'm saying is that after blowing up, so there is a hypersurface, so there is a ruled surface. So there is a ruled surface. Yes. With a base C. Yes. And then it intersects. So maybe well, like that. So we assume that okay, C is in the base. A generic line intersects X at 2 points. Okay. So you see, if there is a tangent,
Wait, why you were
Sorry?
saying that they're trisecond, right?
no, yeah, okay. Or you can do the same with seconds. Yeah. You have at least 2 points. Yeah? So then there is a curve. But now you see what is this? So you can think about it. You blow it up and you obtain here. But this is negative boundary. So we know that there is a negative curve here. And there is a P1 vibration, basically linear vibration or something, which is positive. So as soon as you have a positive curve here, so all curves outside of that are positive. So therefore, if there are several components, they intersect upon, or there is a tangent line. So there is always some line which has multiplicity 2, at least greater than 2, and that means for that line, this line in x, so this is here Lx. 2 or multiplicity 3. So therefore you can use, and this is argument which tells you how to kind of extend Zach's result to many other cases. You know, positive curves. How to say? If you have positive curves, there are some tangent directions. There is a bit of I'll say you needed to do something about technicalities about triple tangent, but that can be done. Triple tangent. Okay. So what? Unfortunately, so I initially I thought that it would all be trivial, but then there were problems with high codimensions. So when you look at 3-second varieties for higher codimension, the best results are for codimension 3, and then the results degenerate quite too quickly. However, I think for me it was interesting that this kind of Zach argument, and for me it was a way to understand Zach argument. Yes, that you have a kind of natural negative section, and every section outside which doesn't intersect it has to be positive, essentially positive, and that's. For me, that sounds better than the usual tangent line. And also, for me, I also think that it's kind of interesting to understand what actually happens here, what actually happens on that side. So, in particular, you see, while we don't know exact answer, we know the extreme answer in the tangents, in the case of simple tangent problems, which also were given by Fedor. So that if you have a variety of sufficiently big dimensions such that such that P of T subjects, then we have dimensionless, and then we know exactly on the boundary we know exactly the counterexamples. on the boundary. It's force varieties, yes? Correct. However, here, in this strange question, we also have a potential answer. That whenever you do this sufficiently many times, you are getting an intersection of quadrants. And I wrote many pages on this, but then it never came to conclusion. But I think it is interesting variety. It's a rare case when you have a non-trivial tangential question, let's say about tangency map, which potentially has a good answer. Intersection of quadrants and only intersection. You know, I'm kind of. That's all I wanted to say. I think nobody will complain about the long debate. But if you have questions, I will be glad to answer.
Well, suppose you spoke in of the dimension 2. Suppose that you knew that Fatron conjecture was correct.
Yeah.
So will it facilitate much your answer?
Maybe. Okay. That's another thing to do. You know, I must say,
Is this conjecture true for complete intersection? Please.
I hope so. I don't know. Already, you know, so here, what I want to say is that since I am usually optimist, I kind of was looking for solution of the conjecture in a whole. Yes, but then when it didn't converge, I didn't do many simple cases. I just moved to something else. So therefore, there are many. I think it's an interesting subject which combines together, you know, the plane geometry, the kind of projective geometry, pure projective geometry, which is, let's say, slightly different subject like symmetric tensors. And all these questions would be nice to get a clear result. And potentially there is a clear result. So, for example, we know that for dimension 2, we know that there's exactly two intersection of two quadrants or something.
And what examples of the boundary do you see?
No, I don't know. I think, for example, if you take iterations here, yes, if you consider iterations here, so several iterations, so take this, then again you have to define precisely. You have to use only smooth points, basically. Then if you take it several times, then you're getting something like intersection of quadrants. I think always. OPN. So in fact, you can say, so from what I was saying, we are looking only at part of symmetric tensors. So basically, this part of symmetric tensors, so the image of symmetric tensors coming from ON plus 1, yes. So I think this variety, Cx, controls the image of H0 Sm ON plus 1, yes, from into H0 of Sm of tensor.
What is it controls? What?
Controls means you look, if in general, you know, if you have subvarieties, for example, surfaces, if you look at surfaces in P4, then certainly for surfaces in P4 you may have plenty of symmetric tensors already, but they're not coming, they have no relation, or if you tensor 1 you have even more, but they're not the ones which are coming from that side. It's exactly this kind of argument actually tells you that all of the symmetric tensors are existing.
But there is an example of surface, smooth surface in P4 with no trace secant lines through it, of course.
Yeah, that's it. For surface, yeah. I think. Yeah. So no. What I'm saying is that this image. What I want to say is that this image is contained in something like. Well, yes, certainly. You take it once, you get a so you take a surface in P4. You get it once, you have something three-dimensional because you have finite number of lines for every point. Then you apply the same thing to this variety and so on.
And can you say at which step this sequence stabilizes?
I think in this case it will stabilize at the
In
second
this
step.
case,
It will be P4. Yes, so generally P4 or a quadrant. So there are two possibilities. Either it stabilizes. So in general, what I am saying is that this problem, this is related to the image in this space. This space, for example, in case of surfaces, can be much bigger, but nothing is coming. Basically, the statement is nothing is coming from projector space, from this boundary, from this projector. So,
Are you trying to say that the stable thing will always be contained in the intersection problem?
yeah, something like that. You know, the stable, the problem was, and that was a problem which I actually encountered when I'm proving, because, you know, when you take Cx of x, it may instantly become a very simple. And what you're going to use are only lines who kind of similar this kind of tangent line which intersect somewhere only for the smooth spot. So then the problem. So the problem is the beginning of the vector on that level. You can do it for small dimensions, but in general, I don't know how to control. But it's quite plausible. I think it's plausible that there is an answer related to this very general, let's say, tangent. I think it's some kind of problem about tangencies.
Other questions? Okay, participate. Of course, the break will be in 10 minutes, and next talk will start at
In half an hour.
Okay.
and next talk will start at 17:40.
Я на них буду ругать, но расклад. Скажу, у тебя ты только таких физических формул доказываешь, которые получаются ограничения.
Иногда я могу сказать, что только вот когда у тебя есть два условия, тогда только один. Но когда маленькая по размеру, меньше 1/3, тогда только они существуют. И тогда про них как бы ты можешь. Ну, трисекандная форма состоит вот. Мне нужно, чтобы... Вот у меня есть прямая, вот у меня есть через эту трисекандную форму. Мне нужно, чтобы она где-то касалась, имела связь с интенсивностью.
Я понимаю, что ты понимаешь, а оригинал-то в чем?
Оригинал был в том, что я говорю, что всегда, вот если у тебя есть что на самом деле, это результат по поверхности. А все остальные сечения, как бы положительные.